As repeated trials and experiments, we'll have a second example. This example is very important because it allows you to study lots of phenomena in applications like in networking, in optical communication, anywhere that you have various independent events from a huge population occurring in 1D, 2D, or 3D space. Random Poisson points are a set of random points in time, space, and so on. For instance, the time instances that babies are given birth in a hospital, or the location, random location of different trucks, or the time instances that a laser gun produces photons. So you see, these phenomena or these random points are generated by a huge population. The first, for instance, if you consider KGH, the population in Kingston, they are generating babies, and these individuals, they are independent of each other. Or if you consider different truck owners and drivers, they are different entities, so they produce the random location on Highway 401 independent of each other at different times. Or if you consider a huge number of atoms in a laser gun, so they independently, because the number of atoms are huge, so they produce independent points. So you could view these as repeated experiments. So each member of the population could possibly produce a random point or not. Random Poisson points, we generate an example which is not random Poisson points, but then we increase the number of points and the size of population, and then we increase the duration of time, and we reach Poisson distribution. Now, for simplicity, consider that you have a real line. It could be 2D, but for simplicity, consider one-dimensional. And then we consider a time interval from t over 2 and minus t over 2. So if you consider these time interval closed from this side and open from this side, and suppose that these points here, all the points in this interval are equally likely to be taken by first experiment. So a child is, or a photon is given birth to at this point randomly. All these points are, and so this is one point, and then another point here. So we generate n points. We repeat this experiment n times independently. So this will be a Bernoulli experiment. So using the Bernoulli distribution, we can evaluate and write the formulas for this distribution, and then later on we let these t and these n jointly go to infinity, and we'll get Poisson point processes. Let's see how we do it. So consider a subinterval. So consider a subinterval from t1 to t2. This subinterval, I'm asking a question, a very simple question. So I have n points. All the points on this interval from minus t over 2 to t over 2, they're equally likely. So what is the probability that one specific one falls in this interval? So the probability of one of them, probability that one specific points, let's say point 1, is in the interval of t1 and t2. So this probability is equal to, because all points are equally likely, is equal to this length, which is like t2 minus t1, divided by the total length, which is equal to t2 minus t over 2, and is going to be equal to t2 minus t1 divided by t. So this is the probability that one specific point falls here. Now, if I ask you what is the probability that k out of n points are inside the interval of t1 and t2, obviously you will quickly reply that this is a Bernoulli trial, so is equal to n, k chooses n, and then you will get p to the power of k, and 1 minus p. So suppose that k is a non-negative number and is smaller than n, and we denote probability that k points out of n points falls in this interval. So obviously this probability is a Bernoulli experiment, because we assume that every point independent of the other point. So you get this one. And p is equal to t1 minus t2 divided by a. So I could say if I denote t2 minus t1 as ta, these will become equal to ta divided by t. So this is a Bernoulli repeated trial. Now we want to increase the time duration t. So we assume that either k is much smaller than n and ta is much smaller than t. So either you could assume that, or you could assume that n and t, they both go to plus infinity, but the ratio of n over t will stay constant. We denoted lambda, or traffic rate. So either this assumption or these, they both will lead to same mathematical distribution. We will call it Poisson points. So in this case, the probability of k to be in time interval t1 and t2 equal to these can be asymptotically simplified. So you could approximate this expression very easily. You show that if you have this one, or if you have pair of n and t, they jointly both go to plus infinity, and this goes to plus infinity, but the ratio of n divided by t remains constant, then the limit of these will become equal to this number. It will simplify. So remember that p is equal to this number. So this ratio of n divided by t is defined lambda, or traffic rate. So in that case, this interval, which was t over 2 and this minus t over 2, this goes to plus infinity. Obviously this goes to minus infinity. So and then the number of points which are here, n, the number of points that go in this interval, this also is infinity. But the ratio, or the density, so this is the density, number of points per second, because you divide the number of points per second. So this is the distribution. So k here could be 0, 1, 2, etc. K should be obviously smaller than n, but since n becomes infinity, so you have this distribution. So remember that here k could take values from 0, 1 to infinity. So this distribution is called Poisson distribution. And then you could have points on. So the set of points on this real line are these set of points, the random locations, is called Poisson point process. We will learn about these in when we start to talk about the stochastic processes. What are the behavior like distances between them and so on. But right now we know that if you consider any given time interval here with the length of TA, This is probability of having k points in this time interval. Now, if you have two non-overlapping interval, you could write this one. So probability of k points in any time interval of duration Ta is given by that. And here k varies from 0, 1, 2, etc. So this is called Poisson distribution. As exercise, you can define the probability space for this example. For Poisson, so L could be, the possible outcomes could be equal to 0, 1, 2, etc. So it's a set of non-negative integer numbers. And then your sigma algebra is 2 to the power of L, whole combination of that. And probability of getting K is obtained, so you have a probability space. Now, if you consider two non-overlapping intervals, so suppose that you have an interval here, this duration is Ta, and this duration is like Tb. Okay, so what is probability of having K1 in this interval of the first interval? So let's say this is interval 1 or interval A, and this means intersection, K2 points in the interval of A, B. So this interval I denoted by IA, and this is IB. Obviously, TA is the length of IA, and TB is the length of IB. Okay, because the points generated in this interval and the points generated in this interval, they are coming from a huge population, and individual in this population, this individual could be atoms or could be parents and so on. They generate their babies or photons independent of each other. I could say that this is equal to these two events are independent because there is no overlap, so it's going to be probability of K1 in interval IA times probability of K2 in interval IB. And this one I have the expression, this one also I have the expression, so I could write the probability of these two guys. So you get this expression. So the random Poisson points are originally modeled by assuming that these events are independent. So another way of defining Poisson point processes is to say that the random points in any disjoint interval are independent of each other and so on. So in this chapter, we have studied how to deal with combination and repetition of experiments. We have defined the combined probability spaces. We studied the Bernoulli and Poisson point processes. Please read chapter 3.